Now that we've seen a lot of things about cross product, how it's found, what is the algebra behind it, what is actually happening in cross product, the geometrical perspective, let's finally end this topic. And we've also seen a lot of properties of cross product also. Let's end this topic with looking at cross product from physics point of view. Now the thing is, I've just taken two examples to show you where this cross product that you have learned is going to help in physics. But remember, just like your dot product where I took 3 examples, even in cross product where I've just taken 2 examples, these are not the only examples. There are such huge number of examples that it's hardly possible to list all of them here right now. But what I want you to see is I just want you to take a feel of what you have learned and how that's actually applied in physics. So that's the reason why I've taken up these two things these two examples to actually show you what I mean. So first thing is torque. Torque is also known as moment of force. And by the way, if you're not thorough with these terms, if they seem confusing and the concepts behind them and everything seems confusing, don't worry about it, because these are physics topics. You don't need to master them here right now. You just need to understand how cross products knowledge is going to help you in learning these, right? This is called as moment of force. So briefly, if I tell you about torque, so for example, if you have a door which is hinged about this axis, and this door might have some lever which you might just pull with some force F, right? So force is a vector. Now this force, what will happen is it will start rotating this door, right? So this door will undergo some sort of a rotation. So it will cover some angular displacement. So like the door might just come from here to somewhere like this, right? So it might cover some angle theta in this direction. So whenever such a thing happens, where about a fixed axis, you're applying force on some point, it is said that your force is actually producing some torque. It is producing some torque along this axis, right? So let's look at that torque basically. What is the expression for it? So what I'll do is, from here, from this axis, I will draw a vector to this point where you're applying this force. Let that vector be r bar. So you have two vectors now. You have this pink vector which starts from the axis and goes to this point where the force is being applied, and I'm calling that as r bar. And the second vector is your force which is acting on that point, right? This expression called torque has this formula r cross f, r bar cross f bar, right? R bar cross f bar. So just like if I have a block, I have some force. This force causes some sort of an angular, some sort of a displacement, some sort of a linear displacement. Similar to this door's example, this door is covering angular displacement. And because this angular displacement is occurring, I would say there is some torque present. Right? So similar, just the way force is causing a linear displacement, torque is causing angular displacement. I'm trying to find that torque. That's basically r cross f, right? So if you look at this, if you look at how to find r cross f here, this is basically your r right now. This is your f which is pointing in this direction, right? It's pointing in this direction, so it's like this. This is your f, right? So you just make sure that these two are at the same junction. You bring them at the same junction. Then you have to do r cross f through the smaller angle. This is a smaller angle. R cross f is going downwards, right? R cross f is going downwards. That means your torque is a vector which is downwards. So this torque is along the axis but downwards. So it's interesting. This pink thing called torque is causing this angular displacement. That is the understanding that you need to have. And how did I find the direction? I found it using this cross product, right? Which I learned in mathematics. And the formula for that is this. This is all about your torque. Coming to angular momentum. So angular momentum is also something very interesting. You would already know what momentum is, I hope, because you have a mass m having some velocity in this direction. So this is your east, right? So basically your x direction. Let this be x, y and z, right? So let these be the directions. So this is your east. So basically this v I can write as vi, vi cap, right? Because this is a vector which is having a magnitude v and it is pointing towards the x-axis, right? So my momentum is nothing but mv bar I cap, right? This is the momentum. Not mv bar I cap, it's mv I cap, because ultimately it's mv bar. So this momentum is a vector, right? Momentum is a vector just like velocity, and it points in the direction of velocity, because if velocity is towards, because m is a scalar, velocity is your vector here. If velocity is towards I cap, your momentum is also towards I cap. What is this term called angular momentum? That is to be seen. So angular momentum is also something very similar. Basically, you have in the center, imagine a ball is moving along a circle. Imagine a ball is moving along a circle. It might have some velocity in this direction, right? If the ball has a velocity in this direction, what is its momentum? Its momentum is also is in this direction, because momentum is ultimately mv bar. So this is just a scalar, which is positive. Mass is always positive, right? So this is like lambda a bar case, where your lambda is greater than 0. This lambda a bar will point in the direction of a bar, right? So mv bar, mv bar will point in the direction of v bar, and mv bar is momentum, so momentum will point in the direction of v bar. So momentum is in this direction, but because it's pointing in this direction, it's again covering some angle, right? So theta, the ball might come here. After some time, the ball might come here. The velocity is like this. It might cover some more theta. So there is some theta displacement going on, right? So just the way momentum causes linear displacement, angular momentum causes this theta displacement. Now I need to find where that angular momentum is, how it looks like. So for angular momentum, which is denoted by L, just the way torque is denoted by tau, angular momentum is denoted by L. L bar is equals to, let this be your radius vector, r bar cross p bar. This is the formula for angular momentum. So what is this r bar? R bar is very similar to this r bar. Basically, what you have to do is, from the point, you have to draw a vector where your body is. So your body's momentum is pointing in this direction. This is the direction of your p bar, and from this fixed point you draw a vector which goes to the body. That's your r bar. So ultimately I will join r and p. So this p bar and r bar is in this direction, right? The angle between them is like this. You need r cross p, so you will put a screw and you will rotate from r to p through the smaller angle. So you'll rotate it like this, right? If you rotate it like this, it goes downwards, right? It goes downwards. That means your angular momentum is a vector which is pointing downwards. So this vector here is pointing downwards, right? Its magnitude is obviously rp sine theta. You need the angle between these two. You need this theta, right? You need, if you forget about this r now and you bring it here, calling it r, you need this theta. So rp sine theta will be the magnitude of this L, and downward will be its direction. So this is how you find the direction of angular momentum using cross product and using the knowledge of cross product that you have acquired from mathematics, right? A lot of times these vectors, they might not appear as arrows, they might appear in their component forms. As in, you might have r bar as some rxi plus ryj plus rzk, and force also you might have some fxi plus fyj plus fzk. You might not have them as arrows like this. Then how do you find the cross product? So you need to find r cross f. You already know how to find cross product in component form. You will take the matrix ijk. Because you have r first, you will put the components of r in the second row, rx, ry, rz, and then you will put fx, fy, fz, and then you will take the determinant of this matrix, right? And that will give you the cross product. So you might have this form of representation, or sometimes you might have the component form. You should know how to find the cross product in all cases. So this completes the entire thing that we had to cover as far as cross product was concerned, the geometrical perspective, how it's used in physics, how it's actually calculated, all the properties that are associated with cross product, and the screw rule as well. So we've covered everything that is required for cross product. Why I've spent so much time on cross product and dot product is because you'll be actually using this extensively in your physics everywhere. So if you're not thorough with this, even if there is the slightest of the confusion left, everywhere it will start creating you a problem. So you have to make sure that you watch this video, this series again and again, and be thorough with both your cross product and dot product. Let's move on to the next type of product as far as vectors are concerned.